Good morning, everybody. We start the last session of this interesting conference of physical chemistry. And it's a pleasure to introduce the first speaker, Professor Helmut Telle. He worked as a professor in Germany, in UK, and France, and many places, and compared to Spain 10 years ago, more or less. No? First in the University Complutense, and now in the University of Telle, 5 years. And the talk of Professor Telle is a cinematographic title, no? He's an expert in laser spectroscopy application, and the title of the story is Analytical Raman Spectroscopy, the good, the bad, and the...
Thank you very much for the introduction and also the invitation to talk a little bit about Raman spectroscopy, what is good about it, bad about it, and ugly about it. Now, you may wonder why I choose this title, and it goes back into my history of research career as a student and later postdoc and a lecturer and professor, because in the 1970s, when I was a student, actually the spaghetti westerns were very popular. And I was a big fan of that because the bads didn't always lose against the goodies, Clint Eastwood. And basically what I didn't know until I prepared the talk, that actually much of this movie was actually shot here near Madrid in Colmenar Viejo and La Pedriza. So the title makes a little bit sense because it has connection to my history at the present here at Madrid. So basically, let's therefore jump into the matter straight away. And I assume that everybody after lunch is a little bit tired, so I will take it easy on you and try not to use too many formulas and so on, and only want to explain to you a little bit about Raman spectroscopy and what to do and not to do in the application of it. And then the last 3 parts, I will give you some examples on analysis of gaseous samples and analysis of solid samples. I leave out the liquids because I rarely work with liquids, just a little bit. And finally, I want to talk about some exotic applications of Raman spectroscopy. So let's a little bit go into details of Raman spectroscopy. And again, I want to start with general photon-matter interaction, then go to the Raman process itself, how it is realized experimentally, and then one very important issue, which a lot of people tend to forget, is that the process is working with lasers, and lasers are polarized. And therefore also you have to consider polarization in the Raman process. And finally, I want to talk a little bit about data treatment and how you can actually apply Raman spectroscopy as an analytical tool. So basically, in lectures as an undergraduate student, you are taught a little bit about light matter interaction and the basic processes which are very much taught are absorption and emission, so basically fluorescence, and a lot of student experiments are based on these two processes. And basically, these processes are actually that the photon mediates between quantum states, and therefore the photon energy is actually equal to the difference between two energy states of an atom or a molecule. Now, if you go to scattering, then basically you find that the photon is not any longer resonant with some energy states, but simply that depending on the particle, whether it is an atom or molecule, very small, a small particle or a big particle, then you have different regimes of scattering. And it's basically that what you encounter as well, a little bit in Raman scattering, is the first one, because we are talking about atoms and molecules. But what you can see from this here is that the scattering is inhomogeneous in the direction. So you have to be very careful from where you actually observe your scattering, if it's from the front or from the side. And that's also true if you go then to inelastic scattering. And here I only mention Raman scattering. There are other scattering processes which are inelastic. And what we find here is that if you have a molecule, and the Raman effect only works with molecules, not with atoms, is that you actually have vibration and rotation in the molecule. And what you find actually in the scattering, that other than in the previous case, where actually the photon does not change its energy, in the Raman process, it does, because it transfers part of its energy into the molecule as rotational or vibrational excitation. So basically, if we now jump into the quantum picture, where we describe the molecule by electronic states, and here we have the electronic ground state, then you have vibrational states which go up and down, and each vibrational state has rotational levels. And then there are various possibilities. One is that you actually have Rayleigh scattering, which I've mentioned before, is that basically the light starts at the same level and goes back to the same level. So it does not change actually energy. As soon as it starts to change the energy level, then you have two processes, which are either that you start at the lowest level and go to a higher level, or you start at a high level and you go to a lower level. And these two processes are called, if the emerging radiation is of longer wavelengths or lower energy than the incident radiation, we call this Stokes scattering, and in the other process, we call it anti-Stokes scattering. And what you have to keep in mind, that the whole thing is actually a quantum process. The whole thing does only work because you have a quantum interaction between the photon and the matter, because we do not have a resonance between two energy levels. So therefore, you start actually at some initial level of the dipole moment, and you go to a so-called dress state, where you have the presence of the energy level plus the photon. If you look at the literature in textbooks, they often call this a virtual level. I hate this because it is not a level at all. It is a quantum entity of the close proximity of an energy level and the photon. It does not work if the two are apart, because then there's no interaction between the system. So basically, you also find that the other than absorption of fluorescence, Raman scattering is a two-photon process, an incoming photon and an outgoing photon. So therefore, that also is replicated in the transition probability, where basically you have the incoming state with the dipole moment, and then from this intermediate dress state to the final state also with the dipole moment. So if you translate this then into the possibility of all individual transitions which are possible between vibrational and rotational states, you find actually that close to the laser line, where you have also Rayleigh scattering, you find pure rotational transitions, which are again of the Stokes and the anti-Stokes origin. And then you also have the vibrational levels in your system, and therefore you produce a transitional, the transition between 0 and 1. You produce a spectrum or a band of transition if you go to the vibrational level 2, and so on and so on. And each time, if you have listened carefully during your lectures, you have the quantum principle. So the higher you go with the vibrational levels, the lower transition probability, and therefore you see that the intensities decrease with increasing vibrational level. And then you have as well the anti-Stokes transitions, which again, because you start at a higher level, which thermally is less populated, so the intensity in comparison to the delta V plus 1 transition is smaller for the delta V minus transition. So therefore, normally, people actually use the Stokes side of the transition rather than the anti-Stokes side. So let us now think about an experiment, how to actually translate this quantum picture into a real experiment. So basically, this is the generic realization of an experiment. You have a laser which comes in, and very often you use a so-called laser line filter, because while you are taught in class that the laser has only one emission frequency, that is not actually correct. It has actually a spectrum of fluorescence from the laser medium, or in the case of, for example, a green diode pump solid state laser, you pump with 808 nanometer, the laser starts at 1064 nanometer, then you double that to 532 nanometers, so have a plentiful of frequency in the system. So basically what you normally do to exclude all that, you put a line filter in, which only allows the excitation laser line to go through. Then you get into your interaction with the molecules. And again, here, if you remember back a few slides, scattering depends on the direction. So in principle, you can, if you want, observe your signal in any direction you want. You only have to be careful that you select a direction in which the emission or the scattering is maximum or best. Then on the detection side, you again have a filter built in which blocks the laser. Because if you look at the transition probability between absorption and fluorescence in relation to a scattering process, Raman, which is a two-photon process as well, the intensities are sometimes 1,000-fold or 1,000,000-fold less than for the fluorescence transition or the laser line. So therefore, it's a good idea to block somehow the laser line entering into your detector. So let's look how then the components of such a system look like. And again, I'll run through this a little bit quickly. If you want more information about this, read some books. And I recommend my book, out of which this figure actually is, Laser Spectroscopy and Laser Imaging from 2018. And so basically what you see, you start with your laser, you clean your laser, and for the actual laser radiation only, you control the polarization. Then you have the interaction, and in most systems you are using in reality, there are three observation geometries. Either you look from the front, so at 0 degrees through your laser, or you look to the back, so at 180 degrees, or you look at 90 degrees, where mostly 90 degrees is a better idea, because both in forward and backward direction, you have to struggle against laser light. And if your laser light is 1,000,000 times more intense, you may drown in that laser light. Then again, you use the components I talked about, sometimes also to have more flexibility in the alignment of the system. You use a fiber, so your spectrometer itself can be moved around or be at a distance. Then again, you have this laser exclusion filter, and you send it to the spectrometer, a detector, and a computer. So this is typical equipment. And here is a picture of the system I actually developed in 2004. So it's nearly 20 years now, but which is still working. I took it with me from Swansea, and it's now here in the laboratory. And this is a picture out of the laboratory here at the Autonomous. So basically, these systems are working very well. And of this type, there are now quite a number of systems working in Germany, Britain, and here in Madrid. So I probably should have commercialized the thing, but again, I'm a scientist, not a businessman. Now, we talked briefly about the excitation laser and that it is not resonant with any transition between energy levels. So in principle, you are free to choose whatever laser you want. And in that respect, I have noted down here 3 possibilities. One is to go to the UV below 300 nanometer. And the reason why this is attractive is that most molecules fluoresce only above 300 nanometers. So you're free of the problem of fluorescence. The drawback is UV lasers of substantial power are still rare and very expensive. So basically, what most people actually choose is a laser in the visible, in particular 532 nanometer, because these lasers now come in dimensions of fitting into a hand, but still have multi-watt output powers. And again, the drawback for that is that your Raman signal, these lines here, is overlaid by fluorescence from any other thing you have in your system. Like, for example, you have a sample cell. The sample cell has glass windows, and glass windows fluoresce. So basically, you have to struggle about fluorescence and should avoid it as much as possible. And finally, if you go into the infrared, then lasers are easily available there because they are basically the fundamental of the green laser, and therefore they're even cheaper as 532 nanometer lasers. But the problem is that the Raman signal is proportional to the force power of the frequency. So that means that basically, as is shown here, if you take the 532 nanometer signal as a reference and call this 1, that you increase the Raman signal by a factor of 16 if you go down by a factor of 2 in wavelength, but you decrease it by a factor of 16 if you go to the infrared. So you're struggling then to detect a signal because already the Raman signal is small. Infrared detectors are not very efficient, but it actually works and you're completely free of any fluorescence. Well, some people working in the biomedical field will tell me, well, this is not true because we also have fluorescence in the infrared. But for the purposes of Raman spectroscopy, mostly it does not play any significant role. Now we jump to the point I mentioned at the very beginning, and that is actually polarization. And so basically I've drawn here a few molecules with their dipole axis. And if you are in the gas phase, these are at random positions. So basically you'll find that if your photon is to interact with your laser and the polarization, you find that it interacts little with that one, a little bit more with that one, and so on. Basically, if you look at your Raman intensity, this is proportional to the cosine of the angle between the dipole moment of the molecule and the polarization of the laser. So the worse the matching is, the worse your signal is. So basically, now a few formulas, I cannot spare you that, are actually, if you look at the polarizability, because it is basically that the laser field induces the dipole moment. So basically, you have to look at the polarizability of your molecule. And basically, if your molecule is asymmetric or has different forms, then you have actually different contributions in all three spatial dimensions of the system. And so basically, you have an average polarizability and an anisotropy, meaning that depending on from which direction you are looking at the system, your polarization is not equal in all directions. Basically, this is sort of a paper exercise, which people know from experience that it's correct. But if you want to measure it, that is not an easy task, because as I mentioned there in the slide, directly accessing the polarizability by an experiment is very difficult indeed. But I give you a few guidelines how you actually can access this a little bit, and that is because you have to look at the transition matrix element, meaning what the matrix element you saw a few slides ago, the quantum state, the dipole moment, and the laser photon. If you all put that together, then you find that the transitional moments depend on the actual excitation, which is the first index here, and the observation of your system. And basically, if you have a situation in which there's an error here because it's correct. So basically, you have the situation that the excitation polarization is equal to the observation polarization. In the second case, the excitation is perpendicular to the observation. And what you find is actually that in the first case, there is an additional factor, which is called a square here, related to the average polarizability. And this can be sort of a factor up to 50 larger than the anisotropy contribution. So it shows you that if you get your observation configuration incorrect, then you lose probably a factor of 50 in your signal strength. And I've encountered this with some students back in Germany who said, we do not observe the signal. It turns out the polarizer, lo and behold, there was a signal. And that's simply because of this factor here. So then you see that if you delve deeper into the theory, and there's one of my students back in 10 years ago who actually did the complete theory of how to observe the various signals, and he came up with all the polarizations and so on now. So again, I do not want to delve into details, but only sort of go back to the observation which we do. We enter at 0 degree, we observe at 90 degree in the plane of scattering, and then actually in these formula, the cosine and sine square factors are either 0 or 1, and we basically, from the two signals we have here, we have actually the simplified transition probability, which I have jotted down here. And this sort of measurement of the so-called S-pole, which is perpendicular, and P-pole, which is horizontal or parallel. If you use these two measurements, then you actually have a very good idea how to actually, on the one hand, learn something about your molecule itself, which is the so-called depolarization ratio, which tells you something about the magnitude of the dipole moment, and you have spectral contributions which are only proportional to the homogeneous contribution and the contribution which is the anisotropy contribution. And this helps you a lot in the identification of complex spectra, because you can switch off and on contributions in your spectrum and we will see one of the other examples later on. Talking about data treatment, if you take Raman spectrum, you normally, other than in fluorescent absorption, you do not only acquire your sample for milliseconds or less than a second, but very often you wait minutes. And modern CCD detectors are actually prone that they also actually accumulate not only your signal here, but contributions which come from outer space, meaning cosmic rays. And if a cosmic ray strikes your detector, it generates a flash of light, and therefore most often in your detector you have spikes. And I do not know whether it is visible from the distance. In this raw spectrum you see some dots here, and these are contributions from cosmic rays. So any software which you have should remove these cosmic rays. Then you also find with small detector systems that any optical system has optical errors, and the major error in spectrometers is so-called astigmatism, so that your slit in which you enter at the your spectrometer, which is a straight line, on your detector, it becomes a curved line. You see that sometimes on photos which are taken with wide-angle lenses, that your image is actually distorted, and it shows actually curvatures of the straight line of a high-rise, for example. So the same problem you have in spectra as well. Oops. Then you actually add up all the rows of your detector, you get a raw signal. Then you have, if you have fluorescence, which is nearly unavoidable, you remove the background, and then later on you do some fitting of these lines to extract quantitative information. And this is a program we developed actually some 10 years ago for the Catherine, which is Catherine accounts for a Tritium neutrino experiment. But this program is now used in many groups, including ours here in Madrid. So basically, what can we actually learn from these spectra, which I have briefly explained how they are produced? So basically, there are a lot of things you can extract from it. From the wavelength, you get actually information about the energy level structure. So like in absorption spectroscopy, fluorescence spectroscopy, you can determine the rotational vibration energy structure. But you also, since every molecule has a different energy level structure, you can tell from how far away from your excitation line the signal is, what component it actually was. Was it oxygen, was it nitrogen, and whatever. Then from the intensities, you can learn something about the concentration of the species, because the more particle your laser interacts with, the larger the signal. So from the intensity, you can say if it's a large signal, there were lots of particles. If it's a small signal, there were very few. And then from the depolarization spectrum, meaning that you measure the two components, you can get information about the transition Raman function, but also in a complex spectrum, it helps you to separate various components, because one molecule may depolarize and the other not. So one disappears the signal and the other not. So you can basically switch on and off some of the components. And again, we will see an example later on. Are there more things? So basically, as an analytical tool, if we take all this together, here is a spectrum taken from an experiment in Karlsruhe about 2 or 3 years ago, where basically you find that if you look at the intensity distribution and the factors which go into it, you find that once you have the wavelength or wave number information, and you have the density information. So you can get 2 bits out of the spectrum, And in addition, you find that basically Raman works with any sort of material, be it a gas, a liquid, or solid. And I will only give examples of gases and solids here, because otherwise I would still here at midnight to give you one or the other example. And the other interesting points are that the measurements in contactless, so we can be at a distance. It can be done in situ, meaning that if your system is, as you saw previously in the experimental equipment slide, with fiber optics, your spectrometer can be very far away from the actual measurement location. It can be done in real time, because again, if your system is sensitive enough, and again, we will see some examples later on in the talk, and the analysis is quantitative. So you have a lot of things which you can actually do. So Claudius was to say that this is good. So therefore, now let's start with the actual examples. And what I want to address here are three examples, one of ambient air, and I'll show some results we did here in the lab, and then from isotope substitution and monitoring of B cells. Okay, so let's look at a spectrum here of grid air. And what you see is what you expect. There's nitrogen and oxygen, fortunately oxygen. Some days not very much, it's a lot of pollution. But you also can see actually that there is pollution actually in the gas, because you see small signals of CO2 and you also see water vapor. These are just two examples. Basically from this is a normalized intensity, you see actually that the ratio of about 23% of oxygen in air is correct, and also that water and CO2 are there in sort of ppm concentrations. So basically, this is something which is not surprising, but also confirming that basically you can breathe with air. So now let's zoom in on the oxygen part. And here at the upper part, you see a spectrum enlarged a little bit, and what you can see is a beautiful rotational structure, which is related to the delta J plus 2 and delta J minus 2 transitions. If you look at it, they resemble, again, what you probably heard in the undergraduate lectures, either presently or my colleagues a long time ago. And that is, for a Boltzmann distribution, you can actually extract the temperature. And this is actually what we did. And as you can tell here from the result, the fit of such spectra is very good. So we cannot meet actually the values of a high precision instrument, but it is sufficient to give you an answer. This was in the winter, so just a little bit about room temperature, what we had measured. Now, if you look at this spectrum, you see a little bit of asymmetry down here. So if you zoom in further, you still see only a little bit of a blob. However, if you do what I said a little bit earlier, if you actually manipulate your S&P polarization spectra and subtract them from each other, you can eliminate all these rotational lines which you see here. And the only thing left over is the Q branch of any molecule which is in the mixture. And what you actually see down here, hopefully visible from the distance as well, is that in addition to the standard oxygen 16, you see isotopes of oxygen. And here the 1618 isotope and the 1617 isotope. And again, if we look at the relative intensities of these, we extracted out of this some values, and then if you look at the literature, we're relatively close, at least within the measurement uncertainty. One thing which makes the measurement of the O17 a little bit more difficult is that there is an overlap between that isotope and a hot band, meaning a highly vibrational excited state of the mother molecule O216, and that is something which you cannot actually avoid. So there are always some overlaps, so depending on the resolution of your spectrum. But as you can see, it works. Now, before I go into many of the others, again, I show a spectrum from our Karlsruhe experiments, where we work with hydrogen and in particular tritium. And what you can see in that mixture, you have sort of all the possible combinations of hydrogen, deuterium, and tritium. So you see T2, DT, D2, HT, HD, and H2. And again, from this, you can actually say, well, if I look at a mixture of hydrogen, I always will be able to tell what the actual combination is. If you look at natural hydrogen, you see hydrogen is nearly 100%. Deuterium is something like 0.5%, and tritium 10 to the -3 or whatever. Nevertheless, in Karlsruhe, we have the tritium enrichment, and so we see lots of it. So basically, now I want to describe a little bit about what can be done with this sort of knowledge. And it was actually in 2008 that our system had to fulfill the first test in the field, and that was actually for an experiment in Karlsruhe. And if you go to the lab here, you will see that basically it looks exactly like this, because it was a system which was transferred back and forth between Britain, Germany, France, and Spain. So it's a mobile system in principle, and can be used everywhere. So basically, what did we do there? The idea was that in the Karlsruhe experiment, for the circulation of the hydrogen or tritium gas, you need to make certain that it is of constant composition all the time, and that no contaminants are generated. And in the circuit, there is actually either a catalyst built in, or if you want to generate molecules, or a permeator to separate molecules of different things. So this is a system which is in existence in one way or another. This is a simplified version. And here is a picture here out of our Madrid lab. So it looks a little bit like gobbled together from pieces, and that's actually true, because it was built by a student. Nothing against students, because it works. So basically, what we try to do in that experiment is actually fill the reservoirs with different hydrogen isotopes, hydrogen and deuterium, then circulate it, send it to a catalyst, and see what happens to the mixture. Because normally, if you take hydrogen and deuterium together, nothing happens, because it is chemically more or less inert, and for exchange reaction, it takes months to actually generate HD, for example. So with the catalyst, and you know that from other reactions, you can speed up this reaction. So basically, it goes to the computer. We did actually. Where's the cursor? Yeah. So here is our screenshot from our evaluation software. We had evacuated the system, and now slowly we open one of the valves by hand, and you see a signal here appearing slowly. So we open a little bit, and with more, and the signal becomes larger and larger. until the valve is completely open. And this is actually, there's a measurement taken about every 1 second. So the filling is complete. Now we open the second valve for the hydrogen, and basically, again, you see it's a cool branch, and here the tiny lights. The valve was opened, and immediately the hydrogen appears, but nothing happens to the actual relative concentration of the two. Then we actually allow the system to go through the catalyst. And here you see the hydrogen and deuterium decrease, and the mixed isotope appears. Okay, so this is a demonstration that you cannot only determine what is in the mixture, but you can follow more or less in real time. And as I said, it's in second distances. You can follow actually a catalytic process which happens just in a few seconds, rather than a few months, which normally would be the case for hydrogen and deuterium. So in that respect, Raman spectroscopy is a very, very powerful tool to do this, because it does not only tell you about either or components, but the whole lot you have in your system. So again, Flint gave this approval that everything worked actually correctly. And then actually in 2019, actually came our big splash with the system, and we actually made it onto the cover page of the journal with our experiment. And that was actually the first time that actually the Catherine experiment was running with tritium circulation for the first time, and we actually measured the concentration of this circulating gas. So the experiment looks something like this. It's a huge one, because if you look at the dimensions, the picture is deceptive, because the complete length of the apparatus is 70 meters. So you need a bicycle to go from one end to the other. Not as bad as with the accelerator ring in CERN, but nevertheless. So basically, as I said, the gas is coming from a buffer that circulates through the system, and we measure the concentration of the system. But this was during the first switch on, actually in March 2019. So again, to be on the safe side, we did exactly the same thing as I showed in the filling of the mixing system here in Madrid. Slowly open the valve, so to speak, and allow more and more tritium gas to circulate through the system. And what you see here as well is actually that you do not have only constant gas flow, but that because of chemical reactions in the system which go through a permeator and catalyst, you have a change in the relative composition over time until you reach an equilibrium. So again, Clint gave this approval to that. Now, not everything is hunky-dory, because in particular with tritium, which is radioactive, you have the problem that even with non-radioactive gases, you have that hydrogen can actually permeate into the steel walls of the vessel to which is circulating, and therefore coming out again. So there's an interaction between that. But if you do actually add tritium to that, you have exchange reactions which are triggered by the beta decay of the tritium, and therefore you generate not HT, and also it is possible, because each steel contains some carbon, you extract the carbon from the steel and you generate CT4. And this CT4 actually turned out to be very nasty indeed for the experiment, because I stopped here the display because we did that for the publication, that everything was working well, but it was not. When we ramped up to beyond the 50%, there was so much CT4 in the system that basically the injection into the system was through a capillary at cryogenic temperatures that actually CT4 throws out. And you have ice on the surface, and where you want, and blocked the capillary. So basically, as I said, this latest thing, the hydrogen, is not really very healthy. So basically, the idea then was, basically I told people, you have this problem. They told me, no, we don't have the problem. You have to permeate in the way of, because they are nuclear physicists and not chemists. So therefore, all chemistry was out of reach. So basically, what we looked into actually was some of the early experiments from there's an error here that should not be 2020 but 2010. Sorry about that. So basically, we circulated tritium through a test loop for something like 20 days, and unfortunately there's some cutoff here in the display. So there's nothing in the beginning, but after 20 days, you have actually methane generated in the system. So here's something of the concentration. The tritium goes down, Hg goes up, CT4 goes up by interaction with the steam north. So again, bad thing. So therefore, because hardly anything was known about tritium substituted methane, methane we all know, but tritiated methane is something which nobody or rarely had anybody investigated. There back in the 1950s, some description in the literature, but then disappeared because that work was all related to the hydrogen bomb. So basically, everything disappeared behind the fence, and there's no information available. So we started actually with Desi, here from our department, to look into the generation of tritium-substituted methane, and we used a reactor system at Karlsruhe, and in different steps of the generation, you see here that the relative concentration of the various methane molecules replacing one of the hydrogens with tritium, replacing two with tritium, and so on, you end up with these sort of spectra. And then the information is very good, and we presented this during a symposium 3 weeks ago, and in particular, people from the fusion community jumped on us and said, wow, we need this information because we know this will be a problem in future fusion reactors. So what we actually investigate here is very useful indeed. So let us leave the gases now. Gases are basically very often simple, in quotation signs, and let's move to solids. And solids are very different beasts. So you need, on one hand, a little bit of different instrumentation and also evaluation methodologies. And then finally, I will give you a couple of examples of how to apply Raman spectroscopy to solids. And one is graphene, and the other one are some biological samples. So basically, if you look at the system, you find that actually, if you look at a solid in comparison to a gas, your particle density is much larger, and you have interaction between particles, so that makes life difficult. On the other hand, because the particle density is much larger, you need much less laser power. So that's a good thing. But on the downside, again, is that you see that this picture here, that the distribution of particles, like other in the gas, which is homogeneous, is inhomogeneous. So basically what you need to do here is not simply take a spectrum and that's it. No. What you need to do, you have to map your signal and your sample, either to determine that it is homogeneous or not, or to determine the structure by a Raman signal of the whole system. So basically, this is all done in general with Raman microscopes, and there are plenty of different ways of how we can actually do these experiments. And I only want to actually concentrate on the concept of Raman microscopy because that's what we do mostly here in our lab. So basically, the system works more or less like this. Is that you have a microscope into which you couple your laser by a dipole mirror, so that the laser only goes down to the sample, and the Raman, the fluorescent signal, goes through the filter into your detector. And in order to scan your sample, you move it around underneath the microscope. This is done motorized, other than you trying with your hands to move things with micrometer precision. This is probably not a very good idea. But then you actually find that your problem has increased multifold, because for each point at which your laser interacts with the sample, you record a spectrum. So what you end up with in the end is the so-called hyperspectral cube. So where you have the dimensional information, and each pixel point has a spectrum. So how do you actually use this to reconstruct something in your spectrum? So you basically have your cube here. You pull out one wavelength draw and analyze this draw, and you generate a map of the intensity of at this particular wavelength. And then you have to have some reference, because you do not know what you are actually looking at in general. So basically, you take a reference, for example, an optical spectrum by a microscope, and actually you see here there is some relation between that part. Yeah. So let's now apply this to a real example. And you will see that depending on how you do it, your original structure ends up with something which looks a little bit rugged. But that depends on the sampling. So you can sample at different points, very far apart, and basically you may miss your system completely. Or you can do more samples, and therefore these points are the center point of your laser, but the laser is never a point, but has always an extension of a few microns. So if you look at something which has a few microns diameter, actually your illumination by a laser covers not only a point, but a large section. So therefore, your signal reconstruction deteriorates with system errors, which are lenses, which are aberrations, diffraction in the system, and so on. But they also depend actually on your detector. How good a detector is it? How many pixels per centimeter square do you have? But nevertheless, in the end, you can reconstruct a sample picture. So let us look at the two examples I promised you. Over the last 2 years, we developed actually here at Madrid a confocal Raman microscope, which we transferred to Karlsruhe, and it actually has been just published in December of last year, first results from that. And the reason why we constructed something and didn't know buy it, because it was to be exposed to tritium. And you do not want to expose a microscope which costs 20,000 euros to tritium, because then you can never touch it again. So basically, if something goes wrong, you have lost 20,000. So in this way, this is the system here in the lab. We had this enclosed with a protection, so only the microscope objective is exposed to suction. So to exchange an objective, which costs €100, that is feasible. And that's why we built actually the system. And here is an example where we expose graphene to hydrogen. And as you can see, that was at the very beginning when we worked with graphene. We didn't treat this very carefully. And basically, you can see we introduced damage to it, so it broke apart. But you also can see it was dipped into an acid up to here. So basically, this was reacting with hydrogen, the other part. So basically, knowing what you're looking at, you can actually tell something about what you see in the sample. So let's go a little bit into more detail into that. So we did it a little bit more carefully, and we used actually samples from Grafenea, so a Spanish company actually, which produce graphene FET fits. So you have also the possibility to measure currents and resistances and so on. So if you do a scan of this area here, depending on whether you're on graphene or the metal contact or the silicon background of this device, then you see different spectra, either graphene, the fluorescence from the metal, or the silicon oxide peak from the substrate. So basically, you can actually replicate, you can see it quite nicely here, the actual structure of the system. But you also then can zoom in a little bit and look at your graphene in particular. And what you find here is that actually the graphene sample we have here is not homogeneous, was not homogeneous as a manufacturer folder. But you all know who work with graphene that you have defects in the system depending on how you treat it. And if you're close to a contact, then you put stress on the system and there's more defects, and then actually your spectral changes. So basically, again, this proved that Raman microscopy tells you a lot about the composition of the sample, but also the spatial distribution of the individual components. So, good thing. Let's go a little bit further to a system which is even more complicated. Graphene is a pure material. Let's go to a biomedical sample. And here's an example for lymphocyte cell. Again, those who do biochemistry or so probably knows it. But again, you will find in all these organic entities a lot of contribution from different components. So basically, again, returning back to the hyperspectral tube, you can pull different draws of wavelengths, which are associated with various peaks, and you can draw down maps of your cell, and you see the distribution of various components inside your cell. Another example here, where you can follow in real time, so to speak, the separation of a cell. So you start that the cell moves apart, it duplicates itself, and then after some time you can tell exactly that it has duplicated. And the final example from my time in Swansea, when I was director of the Raman spectroscopy group at the Nano Health Centre, we developed actually a methodology for diagnostics in the hospital to distinguish whether a bacterial infection was by different bacteria from the same family, so meaning strains, or even clones, meaning that they have mutated, and therefore you could tell something about whether an infection was new or a recurrence of some infection. basically, if you look at the spectra of some of the three bacteria we looked at, you hardly see any difference. So you needed to do principal component analysis or multivariate analysis, where you compare not only one line as was done here, but the sum of all. And if you did that, then you could actually separate all of these individuals in space or in the parameter space, and therefore you could tell whether it was a different bacteria, for example, Staphylococcus aureus or E. coli, so the small particle, or even if it was a clone, then although the distance was not very large, you still could actually distinguish between the two. So this actually was very interesting for the hospital, because normally, if you look at how people detect or trace bacterial infection, they take a sample from the patient, they do cultivation normally for 24 hours, then they look at the microscope and say, yeah, this is probably this bacteria, but they cannot distinguish between strains. Therefore, you have to do DNA analysis that takes another 2 or 3 days. So until you have the diagnosis back, the patient is dead. So basically, what our goal was to reduce the cultivation time until only microcolonies were generated, and then do laser spectroscopy on that. So basically, after a day of cultivation, within 15 minutes, you have the results. So this had a tremendous advantage, and so was declared to be good. Actually, I left the center before the clinical trials were over, so I do not know it at the moment how far it has progressed into actual analysis in the hospital. But it turned out when we did the first test that about 20% of all samples we got from the hospital were bad, meaning that the person who took the samples put the finger in and did something else to it, they were contaminated, and they put very difficult to analyze. Anyway, so all right. So I want to terminate my presentation actually with some exotic application. That means rather than being in the lab, we go outside of the lab. So basically, rather than having your sample very close to your laser and your spectrometer, you actually send it to a telescope. And telescope can be different in dimensions, so you can look at relatively short distance, like here. And these experiments were done some 10 years ago, and we were also involved in some of these work for the British Ministry of Defence, and that was actually to detect different explosives at a distance without having to take a sample. And indeed, if you again look at two explosives here, TNT and HMX, which are two common explosives, so you would say, well, explosive is explosive. No, it's actually not. If you look at the spectrum, they are quite different. And as you can see here, even at a distance of 30 meters, you could distinguish unequivocally between those systems. And we were even able to measure plastic explosives and tell where they came from, whether they actually came from the Czech Republic or from the United States. Okay, good thing. Now we go a little bit further away. So make our telescope a little bit bigger, and rather than directing it horizontal, put it up. And there were, and there still are, instruments like that are actually observed at many airports these days. And they're actually there to measure actually the development of rain clouds. And here's an example of a cloud cover detection up to a distance of about 10 kilometers. And you see there's hardly anything here. Then comes the cloud, and here's the water vapor density, and so on. And these systems are used today to actually forewarn the airport if there's rain or the torrent developing or fog is developing, because they can actually tell from these spectra, and they take action in real time. And as you can see here, over time, there's an evolution of these water vapor concentrations. Good stuff. And then we go even further away. And probably some of you have read during the COVID time, I had plenty of time, that there was actually a mission by the Americans to have a rover landed on Mars, which had the remit to look for organic materials for traces of life, basically. And this was done. Here's an artist's impression of the system. Had two spectroscopy detectors, one for Raman spectroscopy and the other one for X-ray spectroscopy. So once the system had landed, it actually moved around the Mars surface, not very far, but explored the Jezero crater, and basically showed some results from this area. So the two detectors were used in parallel, and they had similar resolution of space, so that you can put overlay the pictures of those, because as I showed before, Raman spectra, you always have to compare with something else to tell what you see is real. And basically, this is how they actually looked at some samples. With the camera, they looked at the region of interest, which was this sort of formation. And they said, aha, this looks like something which could be a grain of material which may contain organic molecules. And then they did scans of the surface. And indeed, what they were able to do, they observed various peaks, and here's only one example from that publication, and they could actually distinguish in the distribution where individual materials were found in the system. Again, multivariate analysis, not simple looking at one spectrum, that's it. No, you have to look at thousands of spectra. You cannot do that by hand any longer, to use software. And finally, from that, some Raman maps were generated. No light was found yet, but nevertheless, it is quite promising if you use methodologies like this, that you may actually find some good thing. Okay. Also, probably Clint Eastwood did not know very much about space exploration, so we had to ask Spock, and he would say it's less than you got. Okay, with that, I want to finish and not keep you any longer. And thank you for listening. And I have to thank quite a lot of members of my group over the years for doing the work. Thank you.
Now it's time for question or comment.
Yeah, thank you, Helmut. It was very good talk. I have a question related to the studies in transistors structures, the one that shows the graphene layer on top.
Yeah.
Is it possible to observe any difference in the Raman spectra when you apply a bias to the device or a current?
Where is it? Yes, indeed. These are experiments which are currently ongoing. And we actually did the following, that we wanted to measure how much tritium was exposed or absorbed on the graphene. And we did actually, because these devices have contacts, so we did 4-point funded hole measurements. And with that, you actually could see differences in the system. So in principle, that's all possible, but very much in its infancy, I have to say. We just started with that about 3 weeks ago.
Okay.
Because everything with tritium is science fiction. You have to make a case that you are allowed to use the sample and so on. It has to go to the ministry to allow you to work without that. You have to make some application also to the military that they actually say you work with tritium. Is it called involved? You know? So all this is very time consuming, but we have still spectroscopy. I'm writing at the moment the conversation.
And I have another question related to the atmospheric LiDAR thing mentioned. The laser they are planning to use is what wavelength or?
Well, again, they use different wavelengths for this. In particular, very often these systems are combinations of absorption and Raman LiDAR. Now, because the Raman does not tell you, it's difficult to actually penetrate things because the signal is absorbed out or scattered out. Okay? So they use absorption LiDAR then to determine actually thickness of layers. And for that, they do the different layers. So normally these systems are sort of, there's not only one laser, but there's sort of an array of lasers who send the radiation speeds.
Very much, very clear and very excellent. I was wondering if you could comment something about the application in medicine, and in particular, like point of care. I mean, I guess one of the main difficulties or problems of Raman is the low entropy of the signal. With very high sensitivity and very good spectrometers. But I was wondering, for instance, if using surface enhanced Raman scattering that can simplify the detection system and very low.
As I showed in that picture here. So you can do a lot of different applications. You can do surface enhanced, so you can do tip enhanced, so you can look actually at individual molecules in the system. So there's lots of possibilities. Not all of them are yet mature enough, but basically it is confocal Raman microscopy and the raster scan, which are the most mature, and they are actually used already at point of care. I was involved in 2002, 2003 to develop an infrared laser system for microscope manufacture. These systems are now used for cancer diagnostics in British hospital. How long is here? I don't know.
Okay, thank you very much.